I guess we're switching gears a little bit. I'm going to talk more about a more technical topic instead of kind of various experiments. I'm from the Flatiron Institute, which is a new research institute. It's an internal research division of the Simons Foundation. And the overarching goal of the institute is to advance computational science, and we have various centers that are all computational in nature, from astrophysics, which is simulations of the early universe and black holes, etc., to biology, which is anywhere from genomics to neuroscience. We have groups in structural biology as well, quantum chemistry, quantum physics, and computational mathematics, and scientific computing core that I'm part of, which makes all this possible by building the infrastructure and kind of helping with algorithms and implementation of projects. Today I'm going to talk about Ceph, and Ceph is a distributed storage platform, and this is kind of the buzzword slide, and I'll talk more about what all these things mean. It's distributed, scalable, software-defined storage system that aims not to have any single points of failure. It's self-healing, and it's not just a file system, but more a storage platform that supports virtual machines. It can support files. It can support an S3 type object store, Swift and S3 compatible. And it's an open source project, and it's under very active development. It's kind of the new kid on the block in storage land, as opposed to kind of the more established platforms. The overall architecture is based on this bottom red layer, which is a kind of intelligent object store that kind of does all the redundancy, recovery, and storage aspects of things, and then various kind of higher level services on top. You can write applications that directly talk to the object store, and then there is an S3 compatible object interface. There's a block device interface, so you can actually run virtual machines. You can migrate virtual machines between hosts pretty much seamlessly. And then there's a file system that's a distributed file system that's POSIX compliant and supports Linux and kind of high performance. So what does a Ceph implementation look like? From a physical point of view, it looks like the network, which is the green line here, and a bunch of storage nodes that are hooked on the network with a bunch of disks hooked on the storage nodes, and various other management and metadata nodes and lots of clients. And everything else besides this is done in software, so no fancy SANs, fiber channels, iSCSI, fancy adapters with multipath, and not even RAID controllers. Everything else is done in software, so just commodity servers, lots of disks connected, and connected with a good network, since everything will be done over the network. So how does the data get onto a system like this? Well, everything ultimately boils down to objects. So when you have a file, let's say a large file, it gets broken into chunks, and the chunks become objects. And the objects get placed onto the various disks in some way. And that's kind of a uniqueness of Ceph, that there is an algorithm called Crush, which does essentially a random hash, some kind of computation based on the cluster topology and what object you want to store, and it will say, pieces of the objects need to go on this and this disks. When something fails, then the cluster topology changes, and this RADOS, this object layer, automatically heals the cluster and redistributes the data. So what does cluster topology and what do this placement of data mean? Well, it's a flexible definition of how you want to place data. You can choose to replicate data, say double or triple replicate data. You can choose to use erasure coding, which is essentially something like RAID over the network. It's a Reed-Solomon type encoding where the chunks that are, instead of placed on disks next to on the same RAID controller, are placed into different nodes in the network. And you can configure all that in software, how much redundancy you want, based on your needs and safety requirements for data. And you can decide that, I have a machine in this room that I'm afraid that maybe I'm going to lose the whole room. I still want to have my data if I do. So you can define how you place your data and how redundant chunks are placed so that you have the required availability. So you could decide that I want my failure domain to be a whole room or a rack. And if I lose my rack, I still have all the data without losing anything. And once this definition is done, the cluster kind of automatically decides where the objects go and just does what you said in the background over time. The other feature that's Ceph that's nice is what's called declustered placement. And this makes recovery from failures a kind of a very fast parallel process. And I want to talk maybe about that a little bit. So traditionally, if you set up a redundant storage, that might be some kind of RAID array. Let's say you use RAID 6. You put a bunch of disks in RAID 6. What happens when a disk fails? Well, you have to rebuild that RAID to a new disk. And how long does that take? Well, that depends on the size of the drive. In today's drives, which are like 8, 10, 12 terabytes, that's upwards from 10 hours, maybe even a day. And while that's happening, you're somewhat at risk. With RAID 6, you can still lose one more disk, but conceptually, your data is at risk. And also, the other thing that's kind of bad about, let's say, a RAID setup is while you're rebuilding, you're stressing the other disks that you're reading the data from. So you're kind of increasing, in some sense, a possibility of another failure. So now let's say instead of one disk, now two disks fail. Two of these drives fail. At that point, you're one failure away from losing data. Yet it still takes you another 10 to 15 or 20 hours to recover. And then you kind of hold on and say, hopefully nothing else happens. So that's kind of the traditional approach. The declustered approach is that you kind of, as you broke up the data into chunks, you place the chunks randomly across a whole bunch of disks. I have 6 on this slide, but the number could be 1,000. I think at Flatiron we have something like 3,000 drives in our cluster at the moment. So I have like chunks like A, B, and C, and this is a triple replicated model since that fits on a slide. A is placed on 1, 3, and 6, and B is on 3, 4, and 5, et cetera, by some random pseudo-random hashing algorithm. So if you do this, what happens when something fails? So let's say the third drive fails. Well, what happens is that Ceph, or a cluster that implements this, would redo this pseudo-random hash function and decides, A, B, E, and F need another copy or another piece somewhere allocated. So it's going to say, where should we put those? Random hash, figures out pseudo-random hashing. It figures out some spots for all these missing pieces that are on the lost drive. And then you have to make those copies happen. So you still have to copy the data worth, or one drive worth of data, but now you can do it completely in parallel. Because many of these drives will be on different machines, they're connected to different controllers, et cetera. You can do a massively parallel rebuild of the data. So instead of 10 to 20 hours, you might be looking at 1 hour or less to rebuild the drive in a failure. And the more interesting thing is what happens if 2 drives fail. So while you're doing this, another drive fails. What happens in that case is, since data is placed randomly, there will only be very, very few blocks where you are kind of critically close to losing data, right? Because since A, C, E, and F, and G in this particular example all have 2 other copies somewhere else, B is the only block that doesn't have any more replicas. So you're only at critically close to losing data on a very small portion of your whole data set. And how much that data is actually decreases as your cluster gets bigger. So if you have more and more drives, the cluster gets bigger. What's shared between 2 drives actually decreases. And that very small amount of data can be recovered, or at least one more copy can be made probably in a matter of minutes, maybe 5 or 10 minutes. So the amount of time that you kind of are biting your nails that nothing happens is down from half a day to a day to maybe a few minutes. So that's the advantage of the clustered placement which Ceph implements. So after kind of a general overview, this is kind of a very high-level picture. There's more complexity to any kind of distributed file system than this. I want to talk a little bit about our Flatiron implementation of how we went about implementing Ceph and why we chose this and what it gives us. So a little overview of the cluster that we have at Flatiron. Our building is in Midtown, so space and power and cooling, et cetera, is all at a premium. We have a data center in the basement that has about 12,000 cores with a few specialized machines and a few GPU nodes as well. We have a co-location facility at Brookhaven National Labs with another 5,000 cores and releasing the San Diego Gordon supercomputer, which is about 16,000 cores. Storage-wise, we have almost a little bit of everything. We have a GPFS storage for home directories and some GPFS at BNL. We're using Ceph for all the large data set storage for genomics. We have the Simons Foundation has a big initiative for autism research, so we have, I think, probably a petabyte, a couple of petabytes of genomic sequence data from families with autistic children. Astronomy simulations, various versions of our universe, or what the universe could be around there. And we also have some Lustre at San Diego, since they're very familiar with Lustre. So the Gordon setup is using Lustre. So why Ceph helps us at Flatiron? We have a very heterogeneous research community. So everybody's computational, but the types of computations that are done are very different. Astrophysics, there's large, tightly coupled MPI jobs and 100 gigabit fabrics. We have a 100 gigabit omnipath fabric. Genomics processing is generally more high throughput type computing, so lots of parallel jobs that need to read hundreds of terabytes of data and fish out various gene variants, et cetera. We have kind of somewhat odd one-off research jobs where somebody says, oh, I need 50 terabytes on one node because my job only runs on one node, but it will generate 100 million files in the process, and you can't put 100 million files in the distributed file system. Well, we can use a block device and kind of prepare 100 terabyte space for them that people can just use for a week or two and then get rid of it. We're not big into cloud, but you could do VMs as well. We have a few VMs, but that's not really our main bread and butter nowadays. We do lots of external transfers. Simons Foundation doesn't have any labs or any wet labs or anywhere where the data gets generated, so we get our data from our collaborators. So we use Globus and GridFTP and friends a lot. And all this has to work across locations as well. And we need some system that's adaptable. We recently occupied our new building at 21st Street. We moved from our old building to our new building without a downtime of Ceph, so we actually moved the data across the dark fiber between the two buildings over probably a week or so without ever being down. And Ceph, as I mentioned, had kind of, the architecture was a bunch of storage nodes with lots of disks attached to them. If you add more storage, you add more processing nodes. So as our storage needs increase and we add more storage nodes, we add performance also. So since all those nodes serve up data in parallel. And what I think I didn't mention is all these calculations of how the data placement is done are done in the client. So therefore, all the clients can in parallel access all the storage servers without talking to a central node. So not like in NFS, et cetera, where you have to go to one place to ask for something. All the clients can do their calculations in parallel and kind of talk directly to all the storage nodes as they need data. And Ceph actually has a very kind of vibrant community. There are releases every 6 to 9 months with lots of new features. Very easy to get questions answered or bugs fixed, which is sometimes difficult with other systems. And it's kind of an architecturally forward-looking design. So instead of requiring specialized hardware, it kind of takes maybe high-end but commodity hardware and gives you a high-performance storage system out of it. So our current Ceph setup is more capacity-oriented setup. We're struggling with the petabytes. We're using a normal 7200 RPM 8 terabyte drives, spinning drives, so mostly for capacity. We use very dense storage nodes that have 90 drives in them and 2 servers, two blades. And currently we have 17 petabytes of raw capacity and we're running in triple replication, so we get 5.5 terabytes of usable capacity. And we are currently testing moving to a 6+3, potentially a 6+3 ratio code, which would double our usable capacity, since we would be really using 1/3 of the space for parity and 2/3 as usable. And we have on order a bunch more storage nodes, so by the end of this year we will be at about 20 petabytes of usable space, and hopefully won't be so full as we are now. And Ceph serves about 500 compute cluster nodes between the Flatiron building and Brookhaven. And real life, about 30 gigabytes a second was the peak that we've seen for both reads and writes, approximately. Synthetic benchmarks can go up to about 40 or so on these 24 nodes that are live today. So the dense nodes kind of look like this. These are 4U nodes that have those 2 blades kind of stuck in the back and 90 drives in the front. So it's a very dense node. It sticks out so far back that we have to take the back doors of the rack off actually to fit them in. It comes in a big box on a pallet and filled with drives. You don't want to try to lift it. This is another picture of the data center with 10 of these in a couple of racks. So I talked about disaster recovery, and we actually had an involuntary test of that not that long ago. Because when we occupied our new building, we got it floor by floor because there were previous tenants. And we moved in and we thought, well, our whole computer center is in the basement. It wouldn't be such a hot idea to put all the storage in the basement because the place can flood and then we lose all the storage. Computers we could replace, but the storage is really bad. So they put a bunch of the storage nodes up on upper floors. But on one of the upper floors, above us, there was another tenant who left some sink running over the weekend. So we weren't there, and the whole place flooded right above the computer closet. So you had some of the Ceph nodes in there, and water and electricity don't do so well. But because of this possibility that we can store different chunks of the data in physically different locations, since they only have to be connected via network, not via SAS cables or not via short-term cables, we actually lost no data. And here is what one of those drives looked like that came out of a flooded computer, where the inside has lots of power and catches fire. Part of the drive is melted. Obviously, you're not getting any data out. Here, there's even water standing on the actual equipment. So this was our kind of involuntary test of redundancy, which luckily worked out. So with this, I'm going to kind of summarize why would I want to use Ceph and what would stop me from using Ceph. So on one hand, Ceph is a very configurable system. It's all done in software. So it's not, oh, I bought such and such rate controller, and therefore I can't put more of this or less of that, because everything is configured in software and can be reconfigured. So it's very flexible. You buy fairly commodity hardware. You can choose, do I want to have faster drives? Do I want to buy SSDs and then get kind of more IOPS and maybe less capacity, or bigger drives and then maybe less IOPS and more capacity? You get to make those choices pretty easily, and you can change those choices by adding hardware in the future. You get a file system, but you get other things. You get an object store, so if you have things that can take advantage of that, it's great. You get block devices, so if you're on VMs, you can do all that on the same set of hardware at the same time even. And there's a very active community, and exciting things are happening. So those are kind of the pluses. On the other hand, it is very flexible. So that's both the disadvantage and the advantage. You get to make choices. You make the wrong choices, you won't get a good setup. So we learned along the way of these are the things that you should do, and these are the things that are not super good to do. So it's easy to create things that will kind of not work very well and make you unhappy. So commodity hardware you can buy, but hardware choices are still important. You buy consumer grade SSDs, that isn't going to work well on the server, for example. So these hardware choices are important, and there are some tricks. But fortunately nowadays there is commercial support, and there are vendors who are selling solutions or support for Ceph. Red Hat is one of the main players behind the development of Ceph also nowadays. So perhaps these disadvantages kind of will diminish over time. So with that, I'll just ask if there are any questions or anything I could clarify.
Hello. I'm Bala from the Rockefeller University. I have a question. Did you ever consider Swift OpenStack or any other object stores? What made you to decide to start using Ceph?
Well, you can actually run OpenStack on top of Ceph storage. So that was actually the original claim to fame for Ceph, was VMs and object storage. So the file system has become stable much later, even though we are the main users. Our main use case is the file system. But VMs and OpenStack was kind of the original target of Ceph some years ago. Why we picked Ceph? Mainly for flexibility. We thought that since we didn't really know at the beginning what types of researchers will come in a year or two, we picked something that evolves over time, and we can hopefully take advantage of new features as they come along also.
In your opinion, do you think Ceph is more flexible than Swift?
Well, Ceph is not just an object store, right? It's kind of a storage platform that implements an API for like Swift or S3. So, I mean, obviously, big players like Amazon who build their own stuff, if you have that kind of resources, you can do that. But if you need something that you can implement on your own, then Ceph is a pretty good choice for that.
So what do you do for versioning or out-of-band data protection, like shadow copies, basically, so you can recall files if you have what if you have a CryptoLocker event or something like this? Your multiple spread out blocks will not save it then, right? So what do you have a solution?
So meaning if someone erases the data or someone modifies it? Well, for that you have to have backups. That's really the only thing that saves you for those kinds of cases. And we are looking at a tape backup solution that we don't have implemented yet. But the file system supports snapshots, and so there are various things you can do in order to mitigate people inadvertently erasing stuff. But there's no way to recover if there's a massive event that intentionally erases files, then there isn't an easy way to recover. Using snapshots is one way that can help.
Was in your involuntary test, were all the drives in that chassis in the same failure domain?
Yes.
Okay.
Yes. And now we actually, as a result, we even expanded the failure domains to try to have the pieces as far physically away from each other as possible. So even we learned from that and even expanded how we place the actual servers in the building.
But then what's that do to your rebuild time and things like that if they're in vastly disparate places?
Not much, because what we do is we just wire them to a nice big Arista switch, all of them to the same across the building. So we just wire them to the same network. So it seems like they're next to each other because they're just fiber wired to the same network.
One more. Is it the Ceph support using different levels of redundancy on a policy basis? So
Yes. Yes.
say these kinds of files or files owned by this user or something like that, or more
yes.
more equal than others?
You can create separate pools, and you can have different responses. You can even define some subset of machines that certain pools go on. So the placement is extremely flexible. You can you can dedicate. So let's say we built this system, and then we decide we want something that has higher IOPS, and we buy another 20 machines full of SSDs. We can add it to the same Ceph cluster and have policies that this directory lives on those and some other directory lives on something else. Yeah.
Rob Bjornson from Yale.
I was intrigued by the thing you alluded to where you could create local storage, block storage for one node very large and then use it. And I guess I don't really understand. You're still going over the network to the storage nodes, I assume. How does that differ from just using the standard storage? And does it come from a pool of unallocated storage? I've never heard of that, so I'm just curious how it works.
So what the difference is in that case you're creating a normal file system on that block device. So all Ceph sees is a big block of bytes, and you create a file system at like ext4 or XFS or something, and only one node has access to that data, so you don't have to do concurrency control over the network to see who accesses the same file at the same time. So the client can cache that like crazy. So if you do that on a machine which has enough memory, then you can do lots of IOPS locally and kind of flush them out to the back end in big groups. So the kind of small file performance, in this particular case, we had a researcher who had 100 million files that were individual frames of movies coming from a microscope, in fact. And 100 million files is like, makes you cringe, like putting that much stuff on a file system. But in case of a block device, that wasn't really a problem because only one node knew that there were 100 million files, and all the data gets flushed to the back end in kind of much bigger chunks.
So you have, you point out that there's a lot of ways to do a non-optimal setup, both for software configurations and even in your hardware choice, which, especially to somebody who's not a storage expert, might be scary. So can you just comment on the learning curve and how you got to where you are today?
So the reason the learning curve worked out for us is because we started small. Because at the beginning when we started, we really maybe had 10 or 20 researchers, and we had, I would say, maybe a few hundred terabytes of data in total. So we started with small nodes, not these big ones, and the competition at that time, the existing system was HDFS, which wasn't even a POSIX file system. You couldn't actually overwrite or modify files. So anything where you could actually use files in normal processes was an improvement. And right? That you could, and along the way we learned, like we started with a certain brand of more consumer grade drives, and then we, for example, learned along the way that those drives corrupted data. You used 100 of those drives. Every so often there were bit errors that were undetected by the drive, that the bits came back wrong. Ceph has replication, and it checksums, and it was complaining that the checksums don't match. And I was like, Ceph bug, Ceph bug, Ceph bug. And then we ran more traditional testing tools and found, no, not Ceph bug, Ceph bug, Ceph bug, drive bug, drive firmware bug instead. And then, okay, we shouldn't do that. So we learned kind of in small steps along the way as we grew what would be best practices. Nowadays, I think there's more information out there. We started this about 3 years ago, then information was harder to come by, but now there is more adoption. It's a bit easier. I think there are consultants also, and Red Hat, I think, sells solutions also. So SUSE is another big player, so there's some more activity. But it's the same as with almost any storage system or any computing system, that if you just randomly buy stuff that you think is a good idea, it might not work out very well.
And you might recommend not starting out with a 20 petabyte multi-site,
right.
You know.
So if you're building on your own, it's perhaps, yeah, if you start like you're going to build a 20 petabyte system with no experience or no testing. We actually have a small test cluster of old machines that we test stuff out on before applying it to the 10, 20 petabytes of system.
Thank you. Thanks.